Hey guys, welcome to the third alkyne video. So we're going to be dealing with a couple more new reactions in this case. And again, these are similar to stuff we've done with alkenes. Alright, but now we're just applying them to how we do it with triple bonds. Okay? So the first reaction we're going to be covering is something you guys have seen. Again, with alkenes. So remember when we had an alkene, which is this, and we reacted it with HX. Now X was a halogen, so like chlorine, bromine, iodine, just not really fluorine. We would get this carbocation intermediate on the more substituted carbon. In this case, it's equally substituted, so we just picked one. And again, we'd react it with our halogen. Actually, let's keep it as X minus. And we ended up getting this right here. Okay? And so we're going to do something very similar in this case when we're dealing with alkynes. We can do something similar. So let's draw an alkyne. All right, now I'm going to keep it again simple. This is going to be symmetrical. Both sides are equally substituted, and we can get a little bit crazier after we cover the simple stuff. So again, we're going to react it with HX. X is a chlorine, bromine, or iodine. So what's going to happen is the triple bond acts is very similar to a double bond. The initial arrow is going to attack this H, kick the halogen out. So we're going to have, let's count the carbons first. 1, 2, 3, 4. Okay. So we draw a 4-carbon compound, and we're going to add the H. So let's say the H added to carbon 3. Okay. Now that means we just used up one of the triple bonds. So we're going to put a double bond there now. And what we've created is, because we removed that bond from carbon 2, we now have a carbocation there. Now you guys may be wondering, why is there a carbocation on the carbon of a double bond? This is very unstable. So yes, it's more unstable than if we did the alkene reactions and had something that carbocation. This is much more stable. It's a secondary carbocation. This is this secondary vinylic carbocation. So it's going to proceed a lot slower than if we had an alkene. Now what can happen is our halogen X minus is going to attack that carbon, giving us this compound, X, and here's our H. Okay? Now, this is also not as stable. Similar to when we had this sort of enol intermediate, it's not that stable to have a halogen on a carbon with a double bond. Okay? So what's going to happen is, remember, we don't always just have one of these HX molecules in our solution. We always have more than that. So another one of these is going to react. All right? And so now the double bond is going to attack another H and kick that halogen out. But now the question is, where is the H going to go? Are we adding the H to this carbon that already had one and form a carbocation on that carbon, or are we forming the carbocation on the other one? So for that, we're going to have to go back to our friend resonance and take a look. So here's the compound we have right now. I'm going to draw a resonance structure of that. And I'm going to take this double bond, put it onto that carbon. So here's our halogen. So now we have a lone pair on this carbon. Right? There's that lone pair. So that's going to be a negative charge. And we just removed the bond from this carbon. So that means we have a positive charge on it. Now, this halogen has 3 lone pairs it can use to stabilize this negative charge. So it can bring a pair of lone pairs down, or a pair of electrons, form this double bond. So it's going to have this, and it's going to get a positive charge. Here's a negative charge. Right? So you can see that we stabilize our carbocation in that spot. So what's going to happen is it's going to be more favorable for that carbocation to exist than if we did this right here. So let's say I have this. I'm going to draw the arrow of that double bond to this carbon. So now we're going to have halogen, a lone pair, so that gives this carbon a negative charge, and we're going to have a plus charge on that carbon, right? It's not as favorable for this compound to exist because, yeah, we have a secondary carbocation, but it's also secondary carbocation in this case. And this is not that stable because we have this halogen right here with three lone pairs, right? And remember, halogens are electronegative. They carry a lot of electron density. So you have a lot of electron density here, and you have a lot of electron density here, and they're going to repel. Okay? So we're not going to want that. That's not going to be favorable. So the favorable area, the favorable resonance structure, sorry, is going to be this compound, or this one actually. So that means the carbocation is going to want to form in that spot. So what we're going to do is we're going to form our carbocation. So that means the H is going to go here. Here's our halogen, and here's your carbocation. And now here's our other halogen, X minus, and that's going to attack that carbon, giving us this compound. Both of our halogens are on the same carbon. So let's do an example when we're talking with real halogens, not just HX. So let's say now I have this compound. Terminal alkyne. We have 1, 2, 3 carbons. And so in general, because we said we reacted it with more than one of these H halogens, HX, we write your halogen and usually over excess. Okay? And so again, we're going to want to form our most stable carbocation, which is going to be on carbon 2. That's the more substituted one. So here's our 3 carbon compound, the double bond. And let's color the H in blue. So the H added here. Also, remember we had 1H right there. So we still have that 1H. And now we have our blue hydrogen. And here's our carbocation. And I actually didn't even show you guys the arrows, but you saw them before, so it's going to be grabbing this to kick this guy out. So we have this compound, our Cl minus, now is going to attack that carbon to give us this compound. Now we're going to react it with another HCl. All right, and then we're going to react. This is going to grab the hydrogen, kicks this guy out. You're going to form a carbocation now on the carbon with the chlorine. Right, and now we have 3 total hydrogens, 2 blue, 3 and another green on that carbon. And our other chlorine that we just kicked out from before is going to attack that carbon, giving us this compound. Okay? And so now again, like from before, you always want to really be careful. In this case, I gave you guys a symmetrical alkyne right there, and we got one product. But if I had something like this, let's say right there, let me make that better. Now, this carbon and this carbon are equally substituted. So that means that our carbocation is going to be equally substituted and equally stable there or there. So when we write, like, let's say HBr excess, we can get a product on, so let's count carbons first. 1, 2, 3, 4, 5. We're going to react with either carbon 2 or 3. So your product, you'll get 2 of them. It can be 1, 2, 3, 4, 5. The 2 halogens right there. right there. Okay, and so want to be careful when looking at your alkyne. All right, be very careful. No need to get point off because of a silly mistake like that. Okay, and so that's how we would do these like HX reactions, H halogen reactions.